when we study the uncertainty principle in quantum mechanics, we usually study the position momentum uncertainty principle. This states that we cannot simultaneously measure the position and the momentum component of a given system with absolute accuracy, because nature herself puts a limitation to the accuracy of the measurement of these physical quantities. Now, this famous Heisenberg uncertainty principle is a subset of a more generalized principle in quantum mechanics that is not just valid for position and momentum, but also valid for many other physical quantities. In fact, in quantum mechanics, there are pairs of physical quantities which have this kind of a behavior, that if you make a measurement of one physical quantity, it automatically affects the uncertainty associated with another physical quantity and its measurement. So in this video, I want to derive this simple expression where A and B are two physical quantities using the help of what is called the commutator of the operators of A and B. If you're not familiar with commutators, you can check my previous lecture video on what is a commutator of two different operators. And if you understand that, let us start with this particular derivation. So here we have two physical quantities. Let's suppose I have a physical quantity A and I have a physical quantity B, and their operators are given by A hat and B hat. These are the mathematical operators which, when we act on a given wave function or a wave function state, gives us some information about the physical quantity. Now, with respect to a state or a quantum state or a state vector, we can also define the expectation values of these physical quantities and their operators, which is essentially nothing but the inner product of that operator sandwiched between the state vector. So here, let us suppose that psi represents the normalized state vector of a given quantum mechanical system. So these are the expectation values or the average values associated with a certain physical quantity A and B. A and B could be anything, all right? It could be position, momentum, angular momentum, spin angular momentum, energy, time, etc. Now, if we define uncertainties associated with these physical quantities, first I'm going to define what is called the uncertainty operator corresponding to A. So the uncertainty operator corresponding to A is defined in a similar manner that we define error associated with a physical quantity in a data distribution. So if you are familiar with statistical mechanics, whenever you have a data set and you have an average of the data set, then the error associated with the data is essentially given as that particular data minus the average of that particular data set. So in a similar manner, I'm going to define the uncertainty operator corresponding to A as A hat minus the expectation value of A. And for B also, I have something similar, B minus the expectation value of B. I've defined the uncertainties, but we can further simplify this particular expression by doing something like this, where we can take the square of, let's suppose, A hat. So if I take the square of A hat, essentially I'll be multiplying this expression with the same expression itself. So you can think of this as A hat square plus A hat expectation value square minus twice of A hat and expectation value of A. Now keep in mind that whenever we talk about operators, the order of writing the operators are very important, because the operators do not necessarily commute. But all operators commute with scalars, right? And expectation values are what? They are the average associated with a physical quantity. So therefore, they are a scalar quantity, a real number. So scalars commute with operators. So A, expectation value of A is the same as expectation value of A acting on A operator. So now this is what it is. Similarly, we have the uncertainty B square is B square plus B hat expectation value square minus 2B hat B expectation value. Right. Now let us try to find out the expectation values of these expressions. Okay. So I hope that you are following the steps. So if I take the expectation value of a square, right, I take the expectation value of a square, this will become the expectation value of a hat square plus what is the expectation value of a scalar? Is the scalar itself, because a scalar doesn't have a distribution. So this will remain unchanged. And what about this? Again, the scalar will be unaffected, but we have the expectation value of a. And again, multiplied to the expectation value of a, this will give us a expectation value square, which finally gives us a square minus expectation value of a square. This gives us a very simple relationship for the expectation value of the uncertainty of the operator a square, which is essentially nothing but this. Now, here I want to introduce the actual uncertainty associated with the physical quantity. See, this is nothing but the uncertainty operator square. But if I really want to find out the uncertainty which is associated with the actual physical quantity, so here you can distinguish between the physical quantity and the operator in the sense that the operator is going to have a hat, the physical quantity won't have any hat. Okay, so the actual uncertainty is given by square root of this particular quantity, which is del A square expectation value. And if I write it here, this will give you the very famous expression for uncertainty of any physical quantity can be measured using their operators. In statistical mechanics, this is basically known as the square root of the standard variance, which is also known as the standard deviation. And similarly, we also have the uncertainty associated with the physical quantity is nothing but, I can write it in a similar fashion, B operator square expectation value minus square of the expectation value of B square overall square root. These are the definitions, right? The definition of the uncertainty of B, the definition of the uncertainty of A. All right, and here of course the definitions of the expectation values and the uncertainty operators. Now, let's come to the actual proof. To find the actual proof of this particular expression, we are going to use something called the Schwarz inequality, also known as the Cauchy-Schwarz inequality. So this inequality is going to be useful for us in proving the general uncertainty principle. So to understand this inequality, let me give you a specific example from vector algebra that many of you are going to be familiar with. So in vectors, do you remember, if I take a vector, let's suppose v1, and I take another vector, let's suppose v2, then what is the dot product or the inner product of v1 and v2? It is simply equal to the magnitude of v1, the magnitude of v2 cos theta, right? If you are familiar with vector algebra, you know that for two vectors in geometrical space, v1, v2 is equal to magnitude of v1, v2 cos theta, which simply means that the magnitude of v1, v2 is always less than equal to the product of the magnitude of v1 and v2. Why? Because cos theta is always less than equal to 1. In fact, I should say the absolute value of the inner product of two vectors is less than equal to the product of the magnitude of those two individual vectors. This is something that is true in vector algebra. But in fact, this is a very specific example of a much more broader Cauchy-Schwarz inequality, which is valid for all kinds of vectors in a linear vector space with a well-defined inner product. Now we know that quantum vectors or quantum state vectors belong to something called Hilbert space, and they also satisfy this particular inequality. So all the state vectors belonging to Hilbert space, which we define as quantum mechanical states, also satisfy this kind of a property. That means if I take two quantum states, psi1 and psi2, and I find their inner product, then the magnitude of that inner product is always less than equal to the magnitude of psi1 and the magnitude of psi2, which can be simplified by writing that the inner product of psi1 psi2 is always less than equal to, what is the magnitude of psi1? It is the inner product of psi1 with itself. Magnitude of psi2 is inner product of psi2 with itself. This can be further simplified as psi1 inner product psi2 mod square is always less than equal to, here we should have inner product of psi1 with itself and inner product of psi2 with itself. All right, this is the inequality, which is kind of similar to the inequality I discussed about the vector algebra, known as the Schwarz inequality. And I'm going to make use of this in our particular uncertainty principle derivation. How? By saying that this psi1 and psi2, well, we can substitute them the way we want. Let's say that the moment the uncertainty operator of A acts on psi, which is the quantum state of the given system, let me call this as psi1. And the moment the uncertainty operator of B acts on the quantum state, let me call this as psi2. Right? I have not really introduced psi1 and psi2 earlier, so I can suppose that this is what they are. So in that sense, this equation becomes, what does it become? Inner product of psi1 and psi2 means that here we will have del A and del B operator sandwiched between psi, expectation value, mod square is less than equal to psi1 psi1. This is going to give me psi1 del A will come twice, so this is going to be del A square psi, and here I have not psi1, sorry, just psi, and here I have del B will come twice, sandwich between psi, so del B hat square psi. So this is the expression that we have, right? But what is this? This is nothing but the expectation value of the uncertainty operator of A, and this is nothing but the expectation value of the uncertainty operator of B. But I have already obtained the expectation value of the uncertainty operator of A and B, right? So therefore, I can write this as, so this can be written as the expectation value of the uncertainty of A operator and uncertainty of B operator, right? Square root I am going to take to the left hand side. This is less than equal to square root of the expectation value of the uncertainty operator of A and square root of the expectation value of the uncertainty operator B squared. So what is this? This is nothing but the uncertainty of A, and this is nothing but the uncertainty of the physical quantity B. So finally we have this expression del A hat del B hat expectation value is always less than equal to del A del B. That's it, we are almost done. So del A is the uncertainty of the physical quantity A, del B is the uncertainty associated with the physical quantity B. They are related to the operators in this particular manner. The only thing I need to do is simplify this particular expression. Del A, del B, expectation value. So to simplify this expression, I am going to use the concept of a commutator of these quantities, okay. So I am going to use the concept of commutator. So you guys are familiar with the fact that a commutator of, let's suppose, A and B is, so in a similar fashion, the commutator of what is del A and del B, it is simply equal to del A del B minus del B del A. So whenever a commutator is equal to 0, we say that the operators commute. If they're not equal to 0, we say that the operators do not commute. In fact, this property of whether operators commute or do not will directly influence the uncertainty principle. We'll see that at the end of it. Similarly, we have something called the anti-commutator. So if I find the anti-commutator of the uncertainty operators of A and B, this is simply equal to del A del B plus del B del A. Now what if I add these equations? If I add these equations, what will I get? This will get cancelled and I will be left with half commutator of del A del B operators plus half anti-commutator of del A del B operators is equal to del A del B. Let's keep it here. Okay, so let's say this is point number 2 and let's use this in the right hand side and calculate further. But before we move forward, let's try to simplify this particular commutator that we have here, the commutator of del A and del B operators, right? Now remember that I have defined del A operator and del B operator initially in this particular manner. So I'm simply going to substitute these two expressions here and see if I can simplify the whole expression. So this is nothing but A minus expectation value of A and B minus expectation value of B, right? So if I simplify this whole expression, what should I get? I should get this times this minus this times this. So you have A minus expectation value of A times B minus expectation value of B, and then we have minus B minus expectation value of B and A minus expectation value of A, right? So let's simplify this expression. What will I get? AB minus A expectation value of B minus expectation value of A B plus expectation value of A expectation value of B. Let's simplify this expression further. I'll have BA minus B expectation value of A minus expectation value of B A plus expectation value of B and expectation value of A. Because there's a minus sign here, this will become minus, plus, plus and minus. Okay. Now, here we can cancel out various expressions. So A, B and AB we can cancel out. Why? Because as I already said that scalars commute with operators, right? So if I write A expectation value of B, or if I write expectation value of B times A, they are the same thing because scalar numbers can multiply from either side. Similarly, this also gets cancelled, this also gets cancelled, and we are left with AB minus BA. But what is this? This is nothing but the commutator of A and B. So the commutator of the uncertainty of A operator and uncertainty of B operator is the same as the commutator of A and B. So I can substitute this here. So let's do that quickly, okay? So I'm going to substitute this here. Here I can write this expression further as or half of the commutator of A comma B plus half of the anti-commutator of del A and del B is always equal to del A del B. So let's quickly take this expression to the right hand side. So I'll call this expression as equation number 3. So now the equation number 3 becomes, what does it become? Del A del B hat is equal to half of the commutator of A and B plus half of the anti-commutator of del A and del B. Now here I want to take the expectation value because I want to substitute here finally. So the expectation value of the left hand side is basically equal to the expectation value of this expression and expectation value of this expression. All right. Now we are almost near the very end. Here what we are going to do is just take a note of this. What is this? This is the expectation value of the commutator of two operators, and because it's an expectation value, it's a number. It's a scalar number. And because this is also an expectation value, it is also a number. Both these two numbers when added gives you the left hand side. So because we are only interested in uncertainty relationship, I can write this as del A del B expectation value, and let's suppose I'm only interested in the absolute values. So mod will be always greater than equal to, let's suppose, half of the mod of the expectation value of A comma B operator. So the first term. So I'm only keeping the first term here because again, the first term is a scalar, the second term is also a scalar, both of them added gives us this. So the left hand side will always be greater than equal to just the first term, and here we are looking at the positive value, so I'm taking a mod here. Now I want to combine this with this particular expression that we had obtained earlier, where also there is a mod. Okay, so if I write this in this manner, so let's say point number 2 now becomes del A del B, which is the uncertainty of A and B, is always greater than equal to this expression, always greater than equal to the mod of the expectation value of del A del B, right? Which, by the way, is always greater than equal to half of the mod of expectation value of the commutator of A and B. So there you have it. We have finally obtained our expression. If I combine this with this particular expression, finally we have, by the way, the final expression, if you want a much more generalized expression, will be this greater than this whole expression, right? This expression greater than this whole expression. But because we are trying to figure out this more common relationship that we see when it comes to generalized uncertainty principle, so I'm just going to write this common relationship that del A del B, which are the uncertainties associated with the physical quantities A and B, is always greater than equal to half of the mod of the expectation value of the commutator of A and B operators respectively. That's it. This is your generalized uncertainty relationship, which is a much more general principle in quantum mechanics, and it will give you an idea whether various pairs of physical quantities have an uncertainty relationship associated with them. So if you have a pair of physical quantity and their operators A and B, and if their commutator, if the commutator is 0, then there is no uncertainty relationship between those quantities. But if their commutator is non-zero, in that situation, the uncertainty principle will be written in this particular manner. That means somehow the uncertainty relationship has to do with whether the operators associated with two physical quantities commute or not. If they commute, there is no uncertainty relationship between the physical quantities. If they do not commute, then there is going to be some positive value, and the product of the uncertainties will be greater than that positive value. Now I want to quickly show you a few consequences of this principle. I want to show you a few pairs of physical quantities where this generalized uncertainty principle will give us some further special expression. For that, let me rub the left hand side of the board. If you are making notes, you can take a screenshot or pause the video here. I am going to rub the left hand side of the board. So let's quickly look at a few examples. So if I take position and momentum, you guys are already familiar with this. So del x and del px, that should be greater than half of the mod of the expectation value of the commutator of x and px operators. So you guys are familiar with the commutator of x and px operator. What is that? Come on, what is that? I h cross. Scalars, right? You know the mod of I? The mod of I is equal to 1. So therefore, this becomes h cross upon 2, which is the Heisenberg uncertainty principle that we are anyways familiar with. If I do the same with something like, let's suppose, del x, del p, let's suppose y. Here I'm taking del x and del p y. What is this? This will be half mod of the commutator of x and py. Do you know the commutator of x and py? What is the commutator of x and py? It is 0. So therefore, this is equal to or greater than 0. It means nature puts no limits as to the measurement of the x position and the measurement of the y component of momentum. There is no uncertainty relationship whatsoever. Let us look at another example. What if I take angular momentum Lx and angular momentum component Ly? It is always greater than half of the expectation value of mod of Lx Ly operator. What is this? If you are familiar with angular momentum topic in quantum mechanics, then there is a very simple expression associated with the commutator of Lx and Ly. It is I h cross Lz. Again, iota mod is 1. Therefore, this essentially ends up becoming h cross upon 2 expectation value of Lz. What this means is that if in a given quantum mechanical system, the z component of angular momentum has a very high expectation value, that will affect the uncertainties of the x and the y component of angular momentum respectively. And lastly, let me show you one more example. If I take the spin angular momentum del L Sx and del Sy, that should always be greater than equal to half of mod of the commutator of Sx and Sy. Again, you know what is the commutator of Sx, Sy? It is I h cross Sz. But do you know what is the expectation value of Sz for an electron? Because electron has half spin. If you are familiar with spin angular momentum, the expectation value of an electron as z operator is h cross by 2. So h cross by 2 and h cross by 2, this is going to be greater than equal to h cross square upon 4. So the uncertainty in the measurement of x and y spin angular momentum component will always be greater than equal to h square by 4 for an electron. So this is the simple, I hope simple enough, derivation of the generalized uncertainty principle and few of the examples associated with it. Anytime you have to find any kind of an uncertainty relationship between any given pair of physical quantities in quantum mechanics, all you need to know is whether their operators commute or not. If they commute, there is no uncertainty relationship between them, and if they do not commute, you will find some kind of an uncertainty relationship for those two operators and their physical quantities in quantum mechanics. I am Divyajyoti Das. This is For the Love of Physics. I will see you in the next video. Thank you so much. Take care. Bye-bye.